question number 6 on the 12.1 homework. It's about goodness of fit. Here we're asked, we have a situation where we're trying to determine whether, I guess, an accountant has been embezzling funds and using faulty check numbers to funnel funds into an account that shouldn't. And one of the things we know is we know the distribution we should expect to see for first check digit numbers. And so if you go here, it gives you this table. And this is kind of an interesting thing. Like 30% of the time, basically, you expect that the first digit in a check number should be 1, right? About almost 20% of the time, you should see a 2. About 13% of the time, you should see a 3, on and on and on and on. It gets a little bit less and less for each subsequent digit. So it's not strictly random where you'd expect, to see 1/10 of the time. You expect to see more 1s than 9s. Okay. So what we can do to determine whether the checks were kind of just fabricated or made fraudulently is we can see if the checks that this company wrote obeys the distribution, or what's called Benford's law. And so all we have to do is open the data in StatCrunch. Slowly, maybe. There we go. Okay, so here on the first column, you've got all the different digits, and then you've got Benford's law, the probability that we expect to see a 1. Okay, over here, we've got the frequency of what we actually obtained from the company's checks. So I'm going to call this, in goodness of fit tests, we usually label something observed and expected. This is what's observed. And then what we expect to see, right, is the numbers obeying Benford's law. So we expect 30% of the time to see a 1. Now, let's see how many checks there were. There in the problem, it says allegedly 196 fraudulent checks were written. So what we'd expect is 30% of that 196 checks to be start with 1s. So we're going to just compute this for each particular digit. How many times we'd expect to see this digit number. Okay. So to do that, I just go to data, right, compute, and I'm going to use an expression. And my expression, I'm going to build it, and I'm just going to write 196 because there's 196 times the probability in the probability column for each particular digit. And then I'm just going to call the column the expected. This is what I expect to see if they weren't fraudulent. Okay. So I actually expect around 59 checks to start with 1, whereas I only got 42. Now, what we're going to do now is run the goodness of fit test to see if that difference is kind of significant or not. Okay, whether it indicates that there's a good chance some fraud was going on. So I go stat, goodness of fit, chi-square. My observed column is label observed, and my expected column is label expected. And then I just compute. Okay. And so that gives me both the chi-square value, which is, or chi-square, which is right here. And then the p-value is just going to be rounded 3 decimal places, 0.017. 0.017. Check the answer. That's good. And then the decision of whether to, now we have the decision about whether to reject the null hypothesis or not. Let's see. What was it? 0.017? Okay, good. I actually remembered. So now we've got the p-value. We can determine whether or not to reject the null hypothesis. Remember what significance we were testing at. Where is that? Yeah, we chose a 0.01 level of significance. And so this is a little bit higher than the significance that we chose. So even though it's suspicious, right, it's not, you know, it doesn't fall lower than our actual level of significance. So we do not reject the null hypothesis because the calculated p-value is greater than the given level of significance. So we're not going to charge this guy. Okay. So I hope that helps a little bit on this problem.